So far, we've been concerned with descriptive statistics, numerical summaries of data. But in addition to describing data, we can use quantitative information to draw conclusions about our subjects. That's inferential statistics. The basis that underlies these inferences is the study of probability. When you have some random process happening, probability predicts what you'll observe based on the characteristics of the process. Remember the shadow puppets analogy? Probability looks at the shape of my hand and predicts what the shadow will look like on the wall. The flip side of this is inferential statistics, which takes a set of observations from some random process and asks what the characteristics of the process must be, inferring the shape of my hand just based on the shadow on the wall. In this session, we mark the beginning of a transition from descriptive to inferential statistics, which we'll study for the rest of the course. But before we can get there, we have to cover some probability. We'll start with some probability concepts, followed by a section on computing probabilities, and finish with probability distributions. First, the probability concepts. We say that something is random if it's unknown but predictable. For example, flipping a coin. We don't know whether it's going to be heads or tails each time we flip the coin, but we can predict that it'll be heads about half the time. Or rolling a die. If it's a six-sided die, then we can predict that each of the numbers will about 1 time in 6. Or drawing a card from the deck. We can't know exactly what card we're going to get each time we draw a card from the deck, but we can predict that about 1/4 of the time it'll be a hearts, and 1/4 of the time a spades, and so forth. Or picking a name out of the hat. We don't know which name we're going to pick, but we can predict that each name has an approximately equal chance of being picked. Many kinds of random processes can be thought of in simple terms such as these. Each time we observe one of these random events, we call it an independent trial if it's a separate observation of some random process for which the outcome in one observation does not affect the outcome of another observation. So for example, rolling a die twice constitutes 2 independent trials because the number you get on the first roll doesn't affect the number that you get on the second roll. Suppose you're playing a game in which you roll either 1 die or 2 dice. You roll 1 die if your last roll was odd, and 2 dice if your last roll was even. In this game, successive rolls are not independent, since the number of dice you roll depends on the previous observation. We can talk about the probability of a given outcome as the proportion of times the outcome would be observed in a long run of independent trials. For example, flipping a fair coin, if we were to do it thousands or millions of times, then eventually we'd find that the proportion of times you get a heads is 1/2. Or if we're rolling a die, if we were to do this thousands or millions of times, then the proportion of times we get the number 3 would be 1 out of 6. Of course, we generally can't perform a random experiment thousands or millions of times. So we can talk about the long run average. This is the average of a very long run of observations, and it approaches the probability as the length of the run increases toward infinity. It's really important to note that sample proportions only approximate the probability, and the approximation is good only if there's a very large sample size. Finally, for our probability concepts, is subjective probability. This is a personal guess about the probability of something. We see these subjective probabilities all the time. You're talking in conversation with someone, you say, I'm about 80% sure that such and such is true. Or, I bet it was about 60% of the people at that game were wearing orange. These subjective probabilities indicate the strength of our belief in certain facts or events, but they may or may not be very accurate. Second, computing probabilities. For any given random process, we can talk about its sample space. This is the set of all possible outcomes for a given random phenomenon. For example, the sample space of a coin flip is heads and tails. The sample space for the roll of a 6-sided die is 1, 2, 3, 4, 5, or 6. The sample space for drawing a card from a poker deck would be the ace of hearts, the 2 of hearts, and so forth. Think of an urn with 3 balls in it, 2 blue balls and 1 red ball. If we draw out a ball randomly without looking at it, the sample space of this random phenomenon would be blue ball number 1, blue ball number 2, and the red ball. We can also think of the sample space of compound outcomes. For example, if we flipped 2 coins instead of 1, then the sample space would be 2 heads, first a head then a tail, first a tail then a head, or 2 tails. Or suppose we flip a coin and then roll a 6-sided die. The sample space would be a head and a 1, a head, and a 2, and so forth all the way through a head and a 6, and then a tail and a 1, a tail and a 2, and so forth. In probability, we talk about an event as a subset of the sample space. For example, an event might be rolling an even number. The sample space for rolling a 6-sided die are the numbers 1 through 6. The event rolling an even number consists of the outcomes 2, 4, and 6. It's a part of the sample space. Or we could talk about the event of flipping a head. The sample space of a coin flip is heads and tails. The event flipping a head is the subset with just one outcome, a head. Or we could talk about the event of drawing a face card from the deck. The sample space here are all of the cards in the deck, and the event drawing a face card consists of the subset of that sample space that only has the outcomes with face cards, the Jack of Hearts, the King of Hearts, the Queen of Hearts, and so forth. Earlier we talked about the probability of an outcome. We can also talk about the probability of an event. This is the sum of the probabilities of each outcome in the event. For equally likely discrete outcomes, the probability of an event is the number of outcomes in the event subset divided by the number of outcomes in the entire sample space. For example, the probability of the event flipping a head is 1/2, because there's one outcome in the event, the head, and there are two outcomes in the sample space, head and tail, so 1 divided by 2 is 1/2. Or we could talk about the probability of rolling a number divisible by 3 on a 6-sided die. The sample space has 6 outcomes, the numbers 1 through 6, and there are 2 of them that are divisible by 3, 3 and 6. So the probability of the event rolling a number divisible by 3 is 2 out of 6, or 1/3. Or we could find the probability of drawing a face card. There are 52 cards in the deck, 12 of them are face cards. So the probability of drawing a face card is 12 out of 52, or 3/13. What about if we have a compound event? Well, if the compound event is composed of independent events, then the probability of a combination of the outcomes is the product of the probability of each outcome. For example, suppose we think of the compound process of flipping a coin and rolling a 6-sided die. We could talk about the compound event of flipping a head and rolling a number divisible by 3. These two parts of the process are independent. The number that you roll on the die doesn't really have anything to do with whether you get a head or a tail when you flip the coin. So we can find the probability of flipping a head and rolling a number divisible by 3 by taking the probability of each and multiplying them. The probability of flipping a head was 1/2, and the probability of rolling a number divisible by 3 was 1/3. So we multiply them together and we get 1/6. Finally, probability distributions. In probability and statistics, we don't usually just work with isolated probabilities. Rather, we work with a description of the probabilities of all of the outcomes, or sets of probabilities. In many cases, we have numbers associated with the outcomes of a random phenomenon, in which case we can talk about a random variable. This is a numerical measurement of the outcome of a random phenomenon. It could be discrete or continuous. For example, when we roll a die, the actual outcome is the side of the die that's face up, and that die has certain dots on it. Those dots happen to be called pips. We assign a number to each of those configurations of pips that is simply the number of pips that are shown. We could also have a random variable for 2 dice rolled, in which case we would sum the values of each of the 2 dice, or count up all of the pips on the sides that are face up on the 2 dice. Suppose we're flipping a coin 10 times. We could count the number of heads in the 10 flips. Instead of listing the outcome as the individual outcomes of each of the 10 flips, the random variable would be the number of heads out of those 10 flips. Those are examples of discrete random variables. Let's think about a continuous random variable. Suppose we have a random phenomenon in which we select a student from Regis University randomly and measure that student's height. This would be a continuous random variable. A probability distribution, then, is the set of probabilities for each of the possible values of a random variable. If we take the probabilities of all of these possible values and add them together, they're going to add up to 1, no matter what the distribution is, because the probability that something happens is always 1. For example, if we wanted to find the probability distribution for the number of a die roll, we'd first start by writing out the sample space for the die roll, the numbers 1 through 6, and then find the probability for each of these. In this case, the probabilities are equal. They're each 1/6. Suppose we wanted to find the probability distribution of the number of heads in 2 coin flips. Well, this random variable can take on 3 values. You could either have 0 heads, 1 head, or 2 heads. The event getting 0 heads in 2 coin flips has one outcome in it, namely the outcome of flipping a tail and then a tail. The event of getting 2 heads also has one outcome, flipping a head and then a head. The event of getting 1 head in 2 coin flips has 2 events in it, flipping a head and then a tail, or flipping a tail and then a head. So the probability of the event that the random variable is 1 is 1 out of 4. The probability of the event that the random variable is 1 is 2 out of 4, or 1/2. And the probability of the event that the random variable is 2 is 1 out of 4. Just like we could find the mean of a sample, we can also find the mean of a distribution. This is also called the expectation. This refers to the long-run average of a random variable. It's a weighted average of all of the possible values. When we were computing the mean of a sample, we added up all of the observations and divided by the total number of observations. If we had a lot of observations that had the same values, we wouldn't have to add up each of the values individually. Remember that repeated addition is just multiplication. So we could take those repeated values and count them up and find the frequency for each of the repeated values. We could then multiply the frequency of the repeated value by the value itself and then add up those and divide by the total number. This is called a weighted average. And the mean of a distribution is a weighted average of all the possible values of that distribution. So if we wanted to find the mean of the random variable of a single die roll, we would take each of the values 1 through 6 and multiply them by their probability of that value. So we have 1 times 1/6, 2 times 1/6, 3 times 1/6, and so forth. Then we add them all together. This gives us 3.5. What do we divide by? Well, remember, the sum of a probability distribution is always 1, so we could divide by 1, but that's not going to change our answer. The mean of the distribution of a single die roll is 3.5. What about the mean of the distribution of the number of heads in 2 coin flips? Well, we take each of the possible values 0 through 2 and multiply them by their probabilities. 0 times 1/4 is 0, 1 times 1/2 is 1/2, and 2 times 1/4 is 1/2. Then we add them together, and we get 1. If we were to flip 2 coins and count the number of heads we had them, and do that over and over and over again, and then we calculated the mean of all of those experiments, we'd get the long-run average of that random variable, and it would be pretty close to 1. Things get a little dicey with computing the mean for continuous distributions, since the number of possible outcomes is infinite. Exactly how to handle this is beyond the scope of the course. It involves calculus. But let's suffice it to say that the probabilities for continuous distributions come from the area underneath the distribution curve. A very important region of a distribution for statistics is the tail. The tail, or cumulative probability, is the probability of a random variable being greater than or less than some specific value. For example, here's the probability distribution of the number that you get from rolling 2 dice. We could talk about the tail probability of the sum of 2 dice being greater than or equal to 8. We add up the probabilities of each of the possible values of the variable from 8 to 12, and we get 15 over 36, or 0.42.